Yeah, so hello everyone. This is Snigdha, and in this talk, I'll be dealing with one enumeration problem. So basically, what we are trying to do is, given a k-leveled given a polygon with k-leveled vertices, I'm trying to insert non-intersecting diagonals in it so as to decompose this polygon into triangles. And we are denoting this number as ck minus 2. There's a particular reason why I am using this notation, and I will elaborate on it after a bit. So let's just try to look at what we are doing. This is a short animation I made. Here in this video, I have illustrated the number of ways of dividing a k-gon into triangle, and I'm doing that for k less than equal to 6. And so you can see that the numbers are popping up below, like ck minus 2 and k equal to 5. For k equal to 5, yeah. And so this sequence of ck minus 2 is rather special. It's because it appears in a lot of different counting problems, and these numbers are called Catalan numbers. And now this question that we are trying to solve of the finding the number of triangulations possible. This is a rather historically significant problem because on September 4th, 1951, Euler wrote a letter to Goldbach in which, among many other things, he included his discovery of Catalan numbers. In this, he introduced and found a closed formula for them, but the proof of this eluded him until he was assisted by Goldbach and later and subsequently by Segner to complete the proof. So in this letter, he described the closed form formula as this simple product formula. And to be honest, our goal is to find a product. Our goal is to find a closed formula as well. But for now, let's just try to focus on how we can get the subsequent terms in the series, like for larger values of kn. For that, I think a recursive definition is the perfect way to go. So in this snippet, what we are trying to do is we are taking a k-gon. We are taking a k-gon here for illustrative purposes. I have taken an octagon, and we are looking at the triangle through the edge, the k1. That is, I mean, taking the vertices 8 and 1 in here. So we will have another third vertex, and we'll be denoting it by j. Now, for the choice of j, we can take any of the other vertices from 2 to k minus 1. In here, k minus 1 is 7. So yeah, if we remove this triangle, we'll get two smaller polygons, and we can further decompose these polygons with help of triangulation. So one of this is a j-sided one, and the other is k minus j plus one-sided one. So given any triangle through the, given any particular this value of 1, j, and k, there are the ways of triangulating the k-gon are basically the ways of triangulating the smaller polygons. So for the j-sided one, we'll have cj minus 2, and for the k minus j plus one-sided one, we'll have k minus ck minus j minus 1. So we are producting, and we are taking the product of them. So notice that in case we are taking j equal to 2 or j equal to k minus 1, this smaller polygon will basically be an edge. So we need to define the value of C0. We'll be defining at C equal to 1. So now to get the recurrence formula, what we will do is we'll basically sum it over all possible values of j. So we get this. We can make this look a little bit nicer. For that, we are going to use this substitution and just redefine the limits around a little bit, and we'll get this. So yeah, so this expression right here of n plus 1, this is basically the expanded form of the recurrence relation that we got. that we just found. So coming back to a little bit of history, in the late 1950s, Euler suggested Segner this problem of counting triangulations of an n-gon. And now there was a bit of competitive tension between Euler and Segner. And Euler didn't tell Segner anything but the problem statement and the values of Cn up to n less than equal to 7. He didn't even tell the eighth value to him. So Segner accepted this challenge, and in 1758 he wrote a paper whose main result was this recurrence relation. He proved this. We used geometry to solve this. In his paper, he proved this combinatorially, and he computed. Sir, yes, sir. Sir,
Yes.
are you saying something?
No. Sorry. Yeah, you can continue.
Yes. So yeah, he proved this combinatorially, and he calculated the values of Catalan numbers up to 18, but he made an arithmetic mistake at C13, which invalidated his larger values. So when Euler saw this paper, he realized that this recurrence relation was essentially the missing piece that he needed to prove his closed formula for Cn, and he arranged for Segner's paper to be published in the Journal of St. Petersburg's Academy of Sciences. So at that time, Euler was holding a chair in the St. Petersburg Academy, and in that publication, he wrote a summary in which he lavishly complimented Segner and pointed out his mistake, and also computed the values of Cn up to 25. Again, coming back to our question, but to find a closed formula, we will basically need a tool that gets used around a lot, and it's called generating functions. So to be honest, there's a time in your life before you understand generating functions and a time after, and I can't really think of anything that connects both of this other than a leap of faith. So suppose you have a question whose answers are associated with positive integer. That's an enumeration problem you got there. So when you use this sequence to construct a polynomial whose whose coefficients correspond to the terms of this sequence that you have, this polynomial is called a generating function. So let's see what the generating function for our triangulations will look like. So yeah, these are the terms of Cn up to 10, and we are just taking them as the coefficient. So yeah, you get that. So a surprising amount of insight can be obtained by mathematically manipulating and analyzing this generating functions. So let's just try to look what we can do with this generating function for triangulation. So yeah, we are denoting the generating function that we had as gx, and we are squaring it up. This is let's just go for autopilot a little bit, and it will do the thing. It will multiply term by term, and yeah, you got it here. Now, if you'll notice that once you sum this coefficients up, they basically belong to the Catalan numbers as well. So when you expand them out, you can see that this resembles the right-hand side of the recurrence formula that we have got earlier. So yeah, we can just decompose this a little bit using that recurrence formula. There we have it. So notice that this gx and gx squared, they are basically related. If you multiply this gx square with an x and then add in 1, you will get gx. Yeah, so yeah, there you have it. So Now, in his 1970, in his 1751 letter, 1751 letter, Euler found an explicit formula for generating functions, and what he got is actually what we expressed as gx square. And while replying to him, Goldbach made a correction to the first few terms of the Euler's generating function, and gave what we expressed as our gx. And this relation that we got here, this was also pointed out by Goldbach. So this is basically a quadratic in gx. So we will get two roots. Now the thing is, which of these two roots shall we take? So basically the value of G0 is 1. So if we plug in 0 for the root that we are taking for in the left hand side root, we'll see that we are getting some 0 by 0, I think. Sorry, 2 by 0, and the left hand side is 0 by 0. So yeah, you can evaluate these two limits. We can evaluate these two roots using limits, like for at limit at x tends to 0, and we can use the L'Hopital rule, or even we can expand this term of root of root under 1 minus 4x. We can expand it out. So we'll get that the this left hand side limit, that is the one that we are not taking, that the limit doesn't actually hold. That is the right hand side limit and the left hand side limit, they are both different. One is going to plus infinite and the other is going to minus infinite. So yeah, we'll be taking the other one. So to evaluate this, we can basically use this expansion. In here, we'll replace y with a 4x. And so yeah, you can simplify it out a little bit and we'll get this final expression form. So here you'll see that 2k minus 3, 2k minus 5, 2k minus 7, these are basically product of odd numbers between 1 and 2k minus 3. To find a closed form expression, we'll be taking this these two forms of gx, and we'll compare the coefficients of the powers of x. So if we do that, here we need to manipulate it around a little bit. You can rearrange the terms around a little and multiply with a j factorial on numerator and denominator, and it's a fairly simple calculation, and we'll get this last expression that we got, this equality. So yeah, this is what we were looking for. This is basically what we are looking for. So yeah, you saw that how we can use generating functions to solve this problems. This was a discrete problem, and we used a more sort of a continuous, and when we moved to a continuous scale of real numbers, and we used that to handle this problem. So this thing about triangulating a polygon, this is a more of a fundamental problem in computational geometry, because polygons are very flexible and they can be used to model any arbitrarily complex shape. And to be honest, polygon triangulation has got a lot of applications, including in computer vision, in robotics, and image generation, to name a few. So I will highly recommend you guys to check out literature on polygon triangulations and on generating functions. And there's a lot of story to Catalan numbers as well, which is available on the I think on the UCLA site. So you can go and check it out if you are interested. So yeah, that was it. Thank you, everyone.
So thank you, Susmita. So any questions? Yeah, Viral. Any questions? Okay, thank you again. So we can go to the next talk.